Alright, in this video we're going to discuss different activation functions. So we discussed the sigmoid function, and it starts at 1 and it ends in 0. And we all know the problem with the sigmoid function, i.e. the vanishing gradient. So another really popular activation function is a Tanh activation function. And it looks pretty similar, but just like the Relu function, it starts at 1, but the output goes to -1. And the reason why this performs better than the sigmoid activation function is it's zero-centered. And we're not going to get into the details why that works, but it basically allows you to search for more values of the parameters. Although the functions are slightly different, the derivatives basically look the same. And everything in this region is approximately 1. But the problem is when you're in these regions over here, your activation function will produce a very small output. And when you start stacking layers together in your network, you get values very close to 0. So one way to solve that is to use the Relu activation function. And basically, if the input is less than 0, the output is 0. And if the input is greater than 0, the output equals the input. So let's clarify that with an example. So again, everything here is 0. But let's say you have an input of 5. The output of the Relu function is 5. Similarly, if you have an input of 10, the output of the Relu function is 10. It may be pretty tricky to figure out the derivative of the Relu function, but let's plot it out and we'll get a better idea. So here's a Relu function in blue, and here's its derivative in orange. Now as you can see, if we're in the region less than 0, it's 0. But if we're in the region greater than 0, the derivative is basically 1. And at first that really confused me. So if we look at the Relu function at point 1, we see the output is 1. Similarly, if we look at the Relu input at 2, we see the output is 2. So it basically has a slope of 1, hence that plot. So let's look at the different shapes of the activation functions. And they look pretty similar. The Relu function is just has a little weird part over there. But that's not really important. So here's our multi-class neural network with a variable number of inputs and one hidden layer. So as you recall, we don't actually apply an activation function to the final layer. But for the hidden layer, we simply apply the sigmoid as follows. And we can apply the Tanh as follows. And just to note, we're going to change the name of the class. And we can apply Relu activation as follows. So before we go on, let's see how we can create such activation functions using the sequential module. Using sequential, it's pretty similar. We just use nn.tanh instead of nn.sigmoid and nn.relu instead of nn.sigmoid. So let's compare different models. And everything is pretty much the same as before. But this time we'll create a model for each of the activation functions as follows, and we'll train our model, and you can see this in the lab, and we can compare our results. And we see that for the validation accuracy, the Relu and Tanh function performed best, and same with the training loss for the different iterations. So usually they suggest you should start off with the Relu function, because the Relu function is really good for building a neural network, deeper network. So the more layers you have, the more likely that the Relu will perform better. So now that we know about the Relu function, let's see how to build deeper networks in PyTorch. And that's it.